given that internal pressure, pressurized to 90 psi, the wall thickness, 0.25 inches, a quarter inch. And we're given here the internal diameter of the tank is 22 inches. And we want to draw the stress state at A. Right, so to draw the stress state, I'm going to make what we call a stress cube or a stress element, and I'm going to align it with the tank. So if I assign, this will be matched to how I drew my picture. I'm going to say X is the longitudinal direction and Y is along the hoop direction here. So I want to see what are the stresses acting on this little infinitesimal piece of material, and I want to draw the correct directions for all those stress. Again, we're going to see this again in a little bit with combined loading, where we can have multiple things that cause stress in our material, and we look at all of it simultaneously.
We need a z-axis also.
Right, in this case, the z-axis, we ignore the stress through the z-axis, but right, it would be in general coming out of here if we have that xy coordinate system. Right, so what we're going to see is, depending on the orientation, right, we would be concerned about x, y, and z. Right, so what do we know is going to happen since we have a positive gauge pressure of 90 psi? Then this little element is going to be stress. The only thing causing stress in it is that internal pressure. So it's going to be stretched along the radial direction and along the longitudinal direction because of that internal pressure. So it's going to have some stress pulling it along the radius, we call sigma 1, which will also be the hoop stress. And then along the longitudinal direction, what I'm calling the x direction, we're going to have a normal stress due to that internal pressure, which is sigma 2. We're not going to have any shear stresses. We're ignoring the stress that's in the z direction, which is again going to be would be caused by that pressure differential. So really, there's 90 psi in the z direction, but for these problems, we're going to ignore that so that we only have stress along the x face and the y face. So that's what we're going to concentrate on here: sigma 1 and sigma 2. So we know what the stresses are going to be, but we need to find what their values are. So this is where we can use the equations that we just developed. We know that along the radial direction, from the hot dog example, that the stress along the hoop is going to be the PR over T. And then the stress along the longitude will be the PR over 2T. But again, by the way I'm formulating it here, this is going to be, again, internal gauge pressure, the wall thickness, and then the mean radius of the pressure vessel is what we're going to use. Right, so our gauge pressure, 90 psi. We're working in pounds, we're working in inches. The wall thickness is 0.25. The average of the inside or the inside radius and the outside radius. But we can also say it's the outside minus t over 2, or it's the inside plus t over 2, radius-wise. All of these will get us to that mean radius. So in this case, we're given the internal diameter. So we can find the internal radius is 11 inches, and then add half of the thickness. And that will get us our mean radius in this case. Right, so our pressure was fine. That's in pounds per square inch. This is in inches, and now this is in inches. So now we can get what our stress is, which will also be in psi then. Right, so carrying this through, our sigma 1 value, we get 4.01 KSI. Right, so along the hoop direction, it's experiencing 4 KSI of stress. And then we can find how much stress is pulling it in the longitudinal direction by using PR over 2T, because the longitudinal stress is half that of the hoop stress. So we could go through and calculate this all again with 2 over T, but we know it's half as much as sigma 1, so I'm not going to recalculate that. So to 3 digits, the longitudinal stress, we get 2 KSI.